So I thought we would, start by reading it and then looking at part A and giving you a chance to kind of work through it. And once you think you've got a good solution for part A, I want one or more of you, since we're at about, 60% attendance right now? It would be pretty easy to select, I suppose. One or more of you maybe to go up to the board and present your solution. Okay? So if you would, read with me real quick. It says, an object moving along a curve in the xy plane has the position vector x of t comma y of t. Notice they don't tell you anything about x of t or y of t directly, but they do tell you that dx dt is equal to sine of t cubed and dy dt is equal to cosine of t squared. And then it says that at time t equals 2, the object is at position 1, 4. So they do tell us a little bit about position, but they do not directly tell us the position vector. Part A says, find the acceleration vector for the particle at t equals 2. Please note it is a calculator active question, so feel free to use. Once you feel like you have a good solution for A, any one or more than one of you, just jump up to the board and present what you've got. And I think maybe for the sake of those that are not with us here in the room, I might kind of copy what you put on the board via the video, just so they can see it too. But I want to see what you guys have going on. Ready, set, go. Good thing.
Basketball has hurt. I think that's the maddest I've ever It's been in my bag for this time.
Of course, yeah, I need a photograph for that one. So for number 5 here, obviously there's a lot of relationships and things that we looked at somewhat in depth last time. So if you can do this without flipping back to like your, those pages where we develop some of these relationships, that'd be great. But if you don't remember it, you need to flip back, that's okay too. So please do not, listen up, do not move on to B until we have resolved and made sure that A is rock solid, okay? Do not move on to B. So Emma's got a solution up there. What do you guys think? I think Emma has communicated fairly clearly. There's only one thing that she could maybe indicate that she has not indicated. So what's the lone? I mean, I'm not saying that her answer is. I'm not saying it's wrong, and I probably would give her full credit for this. But what's the one thing that, from a communication perspective, she hasn't really indicated? Say again? Yeah, a derivative is involved, right? So the only thing really that maybe could be added here, you've clearly done it, right? But just to indicate that it's a derivative of that vector is what's giving us that. So and that's the only thing I think I could add. Are you guys agreeing with her numerically? And I think conceptually this makes a lot of sense.
Could you write like B prime?
Sure. Yeah, that's just a different notation. Okay. Hi, Cole. You guys have any questions? Emma's done, I think, a really good job. Do we agree with you numerically?
Do we need what you wrote in blue?
So that's what I said. I think if the thing in blue wasn't written there, I think I'm fine with that. I'm saying the only thing that we added from a communication perspective is, hey, I'm doing a derivative here, right? And she obviously did one. You can tell you she did a good chain rule to get there. Sure. You're talking about the vector in terms of t? No, not at all. So like I think you've got to have one of So she, like, if you take away the thing or remove it, we can tell, like someone who has a rudimentary understanding of calculus can tell, hey, look, she did a derivative, right? If you did it your way and you didn't indicate that you did a derivative, like which you did, that you clearly said, hey, I'm doing derivatives, and then obviously you then just plugged in, you're totally fine. You've made it very clear. Totally. Any other questions on it? Okay, please take a look then at B. While I wrote down what Emma wrote, B says, write the equation of the tangent line to the curve at the point where t equals 2. That I mentioned this several days ago. I'm going to drive it home, or at least try to drive it home here. Whenever you are asked to find the equation of the tangent line, the two things you got to have are the point of tangency and the slope of the tangent line. And sometimes when you get into this parametric stuff, or later on when we get into polar type graphs, the tendency is to get confused and be like, oh, the slope of the tangent line, is that dy dt, or is that dr d theta, or is it d theta dt, or dr dt, or whatever. I want to make sure that you understand that whenever you're talking about the slope of the tangent line, you're talking about one thing only. It's dy dx. That's it. So obviously there's going to be a variety of ways that you get to dy dx. I mean, it used to be really, really simple. You got y in terms of x and you do d dx to everything. It was relatively simple. Here it gets a little more complicated because there's y's and t's and x's and t's. Later on there's going to be r's and thetas and t's and y's and x's all mixed together. And what do we do with that? We still are looking for dy dx if we are looking for the slope of the tangent line. Does that make sense? And so Jasmine has done a nice job. She used the parametric form of dy dx, and I'm assuming you guys all did it right in radian mode, and that looks like a pretty good answer. So what do you guys think? Is that good? All right. Moving on then to C. Find the speed of the object at t equals 2. Equals square root of dx dt squared plus dy dt squared evaluated at 2. So it's a little unconventional as far as notation goes, right? You know, it's like on the border of, like maybe if you wrote evaluated at t equals 2, maybe make it a little bit better. It's borderline communication for sure. I think I can understand what you're trying to say, right? We're trying to plug in a 2 for t, right? If you get the t equals 2 now, it's really a lot more. So then, as far as steps go, I think, you know, with the calculator being active, I think the fact that you've got the right relationship up there, and I'm assuming he didn't mess up the calculations. Did he do those right? as far as the calculator went? You agree? Okay, so 1.186. Did you notice there were no units with this particular question? So remember that if there are not units given to you, please don't make any up, right? Don't put meters per second or ubiquitous units per time or whatever. Just leave it.
Distance units per time squared.
Units per time squared or whatever, yeah. Okay, we're good there. Let's move on to part D here. Find the position of the particle at time t equals 1. And for those that are wondering, I think it'd maybe be a little bit more conventional to write it like this. Right, so sine of 2 cubed squared or sine of 8 squared, and this other one, cosine of 2 squared squared. So again, please do show us your solution once you've got it for part D. Find the position of the particle at time t equals 1.
What would you do with that?
For this one, would like S, would that, do you care when you say like S or T?
Yeah, that's definitely best practice to define what your variable stands for.
Okay.
Weirdly enough, I've gone through various stages where I remember why and why I remember don't. Do you remember that sometimes position is noted as S?
Oh, yeah.
Remember that? Like I said, like, very simple. I looked that up, like, oh, that's why someone called it S. I remember now. Well, sometimes it is, it's like a little confusing. If one question, they're saying, hey, find the position of this, and the next one they find speed of that.
Are you kidding me?
Okay. Defined as
Johnny's had a room on his ears, so repeats stuff.
So yeah, best practice is what you said.
That was just him calling you.
Tell me what you mean. Tell me what you mean by that.
Triple brag.
Nobody has the courage to tackle D yet? All right, keep working. Oh.
Nick, remember its position of P.
Got it. I want to write that. I'm taking
Maybe
it.
speak way to your left, Nick, so you get plenty of room. There you go. I don't want Johnny's words crowding you out. See ya.
You guys have more fun, okay?
Oh, you know what? There is something we need to note on Nick's. There should be a dt in there. Like it should be dx dt, dt.
That's what I wrote.
Did you just write dx?
Yeah, dx with no dt, sure. That would be equivalent.
That's what I was just going to write x prime t, and then these guys would be
If you had x prime of t dt, same thing. Yeah, I can live with that.
You wrote S of T, DC.
And I would say, so Nick, I would say from a units perspective, like exploring that I think makes a lot of sense. Because if you think about it, what we're doing here is we are accumulating little tiny changes in position. And so like if the dt's cancel out on both of these, then all you're doing is you're adding up little itty bitty changes in x or little tiny changes in y. And if you add all those little changes summed up to the original position, you'll get the final position. So yeah, from a units perspective, it makes sense. Okay. Ready to wrap this up? We good? Any questions at all? Okay. So I have a little analogy for you, just something to think about. If all of us, and this would be very messy and very weird, if all of us throughout our day dropped breadcrumbs where we walked, right? So all you you have this bag of, and maybe it could be more fun like Skittles or M&Ms or something, but you have this big bag of essentially breadcrumbs, and every second or two, you drop the breadcrumb. You drop the M&M, you drop the Skittle. Obviously, and maybe everybody had their own color, or everybody had their own item that they dropped or something. Obviously, the halls, the classroom, everything would be a big mess, right? Because people are walking everywhere all the time. But if we did that, at the end of the day, we'd see like this, path of red Skittles and a path of green M&Ms and a path of actual breadcrumbs or whatever. And if we could kind of get a bird's eye point of view, just like say at the hallway or maybe out on a sidewalk somewhere outside, wouldn't we see a lot of paths crossing? There'd be a lot of paths, a lot of M&Ms crossing over with Skittles and breadcrumbs, and some people would probably drop hamburgers or something, whatever. There'd be all kinds of paths that cross. So my question to you is, if at the end of the day we looked at all that and we said, man, look at all the paths that crossed here. When those paths crossed, does that mean that two people collided?
No.
Might it?
Yes.
It doesn't have to though, right? What else would have to be true for there to actually be a collision? The T would have to be the same. That's right. So it's not just about, hey, our paths crossed. It's about our paths crossed and were we there at that crossing point at the same time? And if you were, yes, you slammed into each other. Hopefully not too many times. Although if you guys like me walk this hall with all the freshmen, there's plenty of collisions, right? Plenty of collisions. My favorite is when you can see it coming. Like you've got this small, 120-pound freshman with a backpack that probably weighs twice as much as them, and it sticks out like this far, and you can see him about to swing, right in your path. I usually am just like, bam. Stop hitting me with that backpack. Just keep the backpack out of my face, that kind of thing. So anyway, so they're just unaware, right? They just don't know. They're like, whoop. They're focused on their friend or something. So, so guys, we are going to finish by talking about collision points. This will be our final topic, our final example that we need to do here today. And so, let's see here. I want to show you a little calculator here. That doesn't look very good. Let's retry this. Calculator. Hey, there we go. Do not show this message again. Okay, so if you guys would, real quick with me, I just want to do a brief calculator exercise. Check this out. So for our example here, number 6, let's do this. There we go. Okay, so number 6 gives us 2 particles. It says there is particle number 1 and particle number 2, and we get these position vectors. And so I thought maybe we'd start off by graphing these and just kind of seeing what they look like. So I'm going to enter these in here. So I actually got to get to the right mode. I don't think so. I don't think you need. I just want to show you a picture of what's happening, but I think you can. I think you'll see you can easily do this without a calculator, assuming the numbers are friendly enough. Okay, so I am going to write, for my first one, it's going to be t minus 3 for my x component. And for my y component, it's going to be t minus 3 squared. And for my for my second, it's going to be, I guess I'll just put 1.5t minus 4. And 1.5t minus 2. Okay. So then, gosh, I don't know. I'm just going to hit zoom 6 from a graphing perspective. Okay, that works. I basically got a parabola segment and a line segment, right? So what this is the breadcrumbs. So somebody has dropped a bunch of blue M&Ms in this parabolic segment shape, and somebody else dropped a bunch of red Skittles in that linear, like the line segment kind of shape, right? And can you see how the paths cross twice? The question then is, does that mean that there were 2 collision points, 1 collision point, or 0 collision points, right? Because in order for there to be a collision point between these 2 objects, they needed to be at those paths, intersection points, at the same time. Does that make sense? Okay, so let's investigate that a little bit. Take a look at example 6, part A says, determine the exact time or times when the particles collide. So we're going to get a hint about this by thinking about those intersection points. The only way that they could collide is if the x coordinates are the same, or if the y coordinates are the same. So our first step is going to be to set either the x is equal to each other, or the y is equal to each other, and it really doesn't matter which one. So here we go. I'm going to set the x's equal to each other and say t minus 3 is equal to 3 over 2t minus 4. And then I'm simply going to solve for t and see what happens. So if I add 4 over, I get 1. If I subtract 1t, I get 1/2 t. Therefore, t equals 2. So t equals 2 is going to be a potential collision time, right? Potentially what it is. But I need to double check and make sure that the same thing is happening at the y's, right? So I'm also going to, you could do this a number of ways. I think I'm just going to set the y's equal to each other just to kind of point back to our graph a little bit. So I'm going to say, all right, let's set the y's equal to each other. So that would be, t minus 3 quantity squared is equal to 3/2 t minus 2. I'm going to go ahead and FOIL the left side, so it's going to be t squared minus 6t plus 9 equals this. And then it's going to be t squared, and then let's see if you subtract 1.5, so it's going to be minus 15/2, I guess. And then plus 11 equals 0. Something like that. Okay, so then solving this, gosh, could you factor? I'm sure you could factor. But let's keep it simple. If you only use your calculator to solve, it's fine. Give it a shot. T equals. Ooh, the factoring. I don't know. It's going to be nice and fractiony.
I don't think you can, yeah, we can't factor it with whole numbers.
Not with whole numbers, yeah, because that 15/2 is not so good.
signing me.
I don't know if it's gonna work.
I think I cheated and factored it. Yes? I think that's about right. Okay, so when you work to solve this, you would end up with two values. You'd get t equals 2, and t equals, I guess it would be 11 halves. Make sense? Okay. So what we see here then, like I said, this is one way to do this. What we see here, of course, is that when t equals 2, the x and y are the same. So you've got to have the x and y the same at the same time. You can see that that only happens at t equals 2. And so we would say then in a conclusion, we'd say that t equals 2 is when the particles collide. And we'd be done. So on the graph, let's identify which of those two path intersection points are where the two particles collide. So in order to do that, we need to know the position, at least of one of them. So if I plug in a 2 into either of them, I get -1, and that tells us enough, right? So right there, the left one, that's when the particles actually collide. Does that make sense? Okay. Any questions, concerns? What can I do to help?
We don't need to get that equation for this question.
The actual XY?
Yeah.
No, I just said find the times. I just wanted to identify it on the graph. Yeah. Okay. We good? All right, so then the final question here is a nice review question. I'll leave that up to you guys to work on. It says find the total distance traveled by R1. So that would be the parabola. Find the total distance traveled by the R1 particle prior to the collision. Like one-dimensional stuff. Do you guys remember the way that you find total distance traveled is you do the definite integral from a to b of absolute value of v of t dt. Do you guys remember that? And essentially, if you think about it, isn't this right here speed? Speed is the absolute value of the velocity function. And so you might feel like what we're doing here is very different, but it's not. It's the exact same thing, just in 2D instead of 1D. And so for us, we would have the same concept. We'd say, all right, it's the definite integral from a to b, and for us it's 0 to 2, because this particle started moving at 0, and the collision point is 2, right? And then what you put in here is speed, right? The speed just looks a little different in 2 dimensions than it does in 1 dimension. Okay, so then what goes in there, of course, is dx dt squared plus dy dt squared. We're looking at particle 1, so dx dt, oh gosh, dx dt is just a 1, isn't it? So 1 squared plus dy dt, you could do a chain rule, but of course the chain rule factor is just 1. Or you could FOIL it out. There's a number of ways you could handle that. Bottom line, something like 2 times t minus 3 to the first quantity squared dt. Bless you. Bless you again. Okay, so then you run that through Math 9, right, because the calculator's active. What'd you guys get? 3.2? 8.263? 8. 8.268. What do you guys think of that numerical answer? Agree? Any disagreement on that? Okay. All right, so that would be it. We don't need to do the whole baseball one. I always leave that in there as just sort of a, if we had like an extra 15, 20 minutes, which we never seem to. There's always less and less time, but whatever. That's it. So tomorrow when you guys come to class, it will be all about review.